This relatively short video goes over the Part D lecture notebook in the second module on Python basics in the Programming for Data Science class. In this video and in this notebook, we will understand how to visualize data in 2 and 3 dimensions using matplotlib. We will understand some basic plotting options that allow us to resize figures, create arrays of figures, and change how data are visualized. We will also see how to use some built-in NumPy functions for creating regularly spaced input that are very useful for plotting purposes. The notebook has 2 embedded activities as well as a summary activity that you will be asked to complete. As the mathematician Richard Hamming once said, the purpose of computing is insight, not numbers. And the best way to develop insight is often to visualize data. Now, visualization of data can be an entire suite of lectures, or in fact, even its entire own course. But we're going to explore just a few features of Python's matplotlib library in order to get started with this. There is no official plotting library within Python, but this package is the de facto standard. There are many other useful plotting libraries, and some you might even like better or find to be easier to work with than matplotlib, but you'll find that many of them are actually built on top of matplotlib and have just simplified some of the interface that matplotlib really requires a lot of users to get comfortable with in order to use as an expert. Nonetheless, there's a great tutorial to bookmark and peruse, as I provide a link here and I have opened in this other tab. If you scroll to the bottom of this tutorial, you'll find you can actually download it as a Jupyter notebook, and then you can upload it into Colab and explore it from there. I highly recommend you do that along with going through this lecture, just to be exposed to more details. Make it your own. Again, edit things, experiment, not just my notebook, but also this tutorial notebook. And you'll find in a lot of official documentation that there are Jupyter notebooks you can download to explore the things they're showing in the tutorials or basic examples that are provided as part of the documentation. So before we begin, we want to understand the components of a figure and a plot. So Python's matplotlib emulates many features of MATLAB for those that are familiar with MATLAB in terms of MATLAB's plotting, and it uses the same layout for how it creates plots as illustrated below. So first, before we can actually plot, we create a figure, and when we create that figure, you can think of it as like the artboard that's going to contain all the different plots. The plots are going to be contained in the axes. Now we can plot 2 or 3 dimensional plots within a figure. So if there's a 2D plot, there will be 2 axes, an x-axis and a y-axis, and then we could label them using x label and y labels. If you have a 3D plot, then it's called the third axis would be a z-axis, and it would have a z label associated with it. You can title your plots, and there's other annotations and things that we can do, and we'll see some of that more later. But those are the basic components of a figure. So that's just getting started with the basic orientation of what is in a figure versus a plot. So a plot is within a pair of axes or a triplet of axes if it's a 3D plot. And we can have multiple plots, meaning multiple different axes within a figure, so those would be subplots. You can also plot many curves in the same pair of axes as well. So we'll see a little bit of this below. So before we get started, we should import NumPy as NP. I've already run this code cell here, but it's something you should do if you're following along. Now, there's a magic command for plotting in a notebook when you're using different environments other than Colab or even JupyterLab. This is not necessary. But you'll find in some environments, and you'll find sometimes when you're looking at Jupyter notebooks created by other people online, or if you're using something in a traditional notebook setting or other environments, you might need to use this matplotlib inline magic command in order for the plots to actually be shown in the notebook. It's essentially produced as part of the output of the code cell. But they'll be static, you can't really interact with them. Some additional interactivity is capable in certain browsers and in certain environments. If you use a matplotlib notebook magic command, that sometimes allows you to resize a figure, zoom into things, but this is not enabled in Colab, so we can't really use it. So I have this all commented out, but it's here just for completeness so that you're aware that these magic commands exist, and if you ever run into them, just know that they're there so that certain plots display in a certain way. We can use matplotlib inline in Colab. It just doesn't change behavior, so it's completely unnecessary. And if we use matplotlib notebook, the one that I have highlighted as a command in a cell where we're creating a figure, it in fact makes it so the figure doesn't even display, so we can't use it in Colab. So I just have this commented out, but I just want you to be aware of it, know that these things exist. The most important thing about running this code cell is importing the pyplot module of matplotlib as PLT. I've already run this code cell, so it's already imported. And then when you create a figure, you use plt.figure with parentheses there, and that should create an empty figure. So again, this basically creates the figure, but there's no axes. I've run this code cell to say, hey, show me the plot that I've created, except there's nothing to show, and you see that it actually says there's 0 axes there, and that's why you see no output from this other than this information that's related to the figure size, but with no axes to show, there's no plot. So to make a plot, we need to understand some basic commands about the plot command within the pyplot module that I've imported as PLT. So the basic plot command plots x data versus y data. This is very important. That will of course plot y versus x, but you need to make it x data and then y data in the input. Students often do this backwards. It's a very common error for students to want to do y and then x because they think of plotting y versus x. But the y data has to be second in the command. It needs to be x and then y. I cannot emphasize that enough. The default behavior of this command, this plotting command, is to connect data pairs via a straight solid line. If that's not what you want, then you need to change either the line style or the marker style if you want the data to show up in different ways. And we're going to see some of that in this lecture notebook. The np.linspace command is a very convenient command for generating regularly spaced inputs in a one-dimensional interval between A and B. So the idea is that it generates endpoints in the closed interval A and B, and it includes the endpoints, which means that there's n-2 interior points. So this is a commonly used command when you're wanting to generate regularly spaced data so that you can then usually feed it into a function of that data that is then evaluates it at that, and then you can produce a nice graph. So here, for instance, I create my empty figure, and I now create x data. I'm creating 1,000 data points from -pi to pi. I create 1,000 of them. I then evaluate the function x times sine of 1 divided by x for no other reason than to just have something interesting to plot. This creates the y data. I assign the output of this evaluation to the variable y. So then if x right here, that's not correct. I'll just go ahead and rerun this. I've run some other code cells in here. X is now a numpy array. I should hover my cursor over this. Sorry, it's getting a little messy there. It's of shape 1000. It's a 1D array, and y is also a shape of 1000. Now, I can add a title to a plot before or after I actually plot the data. So here I'm using a little bit of markdown text, like the tech of the function, that this is the function f of x equals x times sine of 1 over x, or x to the -1 power. I can control the font size of that. You can play with all of this. I'm actually suggesting that you try changing the font size and also try changing the color of the font. What do you think you would use as a keyword in here to change that? This is something you can look up. You can go through the tutorial perhaps, but try to experiment a little bit with that. How you might think that you can explore changing the title. In fact, there's some parameters here, and you can look at some of the information about the documentation by just hovering your cursor over the title command. Okay, so I've created the title. You can see it's actually displaying here. On that, I'm just zoomed in a lot, and then I plot the data, and then here's the curve that's plotted. So that's kind of it. That's a very simple way to generate the plot. You just create your figure, have your x and y data ready to go, and then you feed it into the plot command of the pyplot module that I have imported as PLT. You can add titles, you can add x labels and y labels, and this is what I'm asking you to start doing in this first activity. And of course, there's a solution video for that. So this is something for you to look at. You can find a solution video on Canvas or in the playlist on YouTube. But I ask you to copy and paste the code cell here into this cell right here. I want you to plot the function using a thicker red dashed dotted curve. I want you to add x and y axis labels and add and edit comments to at least 3 different lines of code to explain what they are doing from what I have here into things that you have to to add to the code in order for everything to work. So that's a good activity, and there's a solution video for it, but it really just gets you started with the basic use of this function, this plot function, and these other things that you can use with it to add different types of labels. I want to make just a few simple points here. This is following activity 1, that there's another way of generating a vector or array of numbers for either computations or plotting, which is to use the arrange function in NumPy. And it's very similar to linspace that we saw above, except instead of producing like a starting and end point, like an A and a B, and then the number of points we use, we specify an increment, which is like a step size to go from the starting value up to, but not including that stop. Notice this is a half open interval. The start value will be included. You will increase by the increment until you reach the stop value or exceed it, but then you won't include whatever that value is. So that's how this works. So I might not know like how many steps of size 10 to the negative 2, so 0.01, that I need to take to go from negative pi to pi. I just know that that's the step size I want to use. So this is a great way to do that. I can just say let x be np.arrange negative pi to pi, and then I can say 1 e to negative 2, which is just this a kind of a more scientific notation way of saying 0.01. But I like writing 1 e to negative 2. So that is different than the np.lins space where I used 1,000 points between negative pi to pi, and they were spaced regularly. To figure out how they were spaced, I would have to basically say, well, it's pi minus negative pi, so 2 pi divided by 1,000. That would give me the actual spacing. And so here, I'm just saying I want the spacing between points to be 1 e negative 2, and I'm not specifying the number of points. That's one of the differences. The other difference, again, being this stopping value won't be included even if it's exactly 1 e to negative 2 away from the previous point that was right before that value. It's just not included. So that's one point I want to make with this particular code cell, and I'm just making a different plot. I'm making the y data be equal to x times sine of x, and you'll notice I'm giving a line style here. This creates dashed lines, and I'm specifying a color with this C, and I'm making it black when I'm using this K for that. You can also say color here instead of C for the color. You notice it's the same thing. There's these shorthand keywords you can use. You can use C instead of color, and instead of line style, instead of spelling that out, you can use LS as a shorthand for line style. And then you can also use, for instance, line width. You can use LW instead of that. So if you're watching this video, which I hope you are when you do this, that's something that you can experiment with the different ways that you can pass kind of keywords into the plot to control various aspects of the plot. Another thing I want to point out is that this plot.figure is actually not technically necessary in the Colab environment. It is in some environments, but we don't need this here. We can get rid of this, and we can run this, and you'll see that same figure shows up. However, I think it's a really good practice whenever you're going to create a figure to actually explicitly create it first. For one, there's great clarity about what you're trying to do in this cell, and also in other environments, like when you're not working in Colab. For me, when I'm doing my research or working in more advanced classes, I'm often using Jupyter Lab on my local machine. That I have installed on my computer. And there, one of the things I like to do is actually track the figure numbers, because as I rerun the cell over and over, it doesn't create a new figure and take up more memory. This can actually specify that this is just the figure number 1, and every time I rerun it, it just replots it over figure number 1 if I'm making changes. If you don't have this in here, even though like if I have that and I run it, in other environments, it might actually say figure 1 here. This doesn't actually say that at all. It's not assigned a number, or it doesn't look like it is according to this environment. But one of the things that you're making sure of if you do this, if you give it a number, is that new figures are not being created. If you leave this off and just run this over and over and over again, it might look like it's the same figure over and over and over again. However, it's usually creating a new figure, and it's taking up more memory every time you rerun it unless you specify this figure number. And I believe that's happening here. We can see I might be wrong. Let's figure this out. So here's this this address, and I think that's the memory address. So I'm just going to go ahead and copy and paste that. I'm just going to comment it here. So let's just put that there. That was that memory address. Now I have this plt.figure, no number there, and if I rerun this and I look at this, I believe that is Yeah, that is different. That is definitely different. So if you look at that number, I'll just go ahead and paste it here so you can see. This is the memory address. A lot of it looks the same, but look here. 5, there's a 4, 7, 8. It's a hexadecimal memory address. So it's definitely storing this. It's kind of the differences are showing up in these last digits between these. It's just being stored in a new memory location. But let's say I go back to say num equals 1. So this is figure number 1, and I create it. Here is now the memory address when I store this as make it as figure 1. It's the 7FFBC846E090. Let's say I run it again. Okay, that's a new memory address as well. I think it should release the information from the old memory address though, in order to I think it's restoring figure number 1 in a new location. So this is important. I mean, you can actually see if you plot over this. So okay, that part was wrong. So the new memory address is still there, but a new figure wasn't necessarily created. And I think it just released. I think it's just stored in a new memory address, but it released the old memory address from what's being stored in the notebook. So one of the issues I have seen this is that if you don't have that figure number here, so okay, I was totally wrong on that, but I'll leave that in the video because you know what? I make mistakes and I learned something there. If you just run this over and over again, it's creating new figures and it's storing them in new memory addresses. I don't believe it was releasing the old memory address for other uses. It's still taking up resources, and I believe that you kind of can keep control of the amount of resources you're using if you specify a figure number. I think I'm dwelling on this too long, so I'm just going to go ahead and move on to this next thing, which is to show you how you can do a scatter plot of a noisy linear function. So here I'm creating this new data x core, just calling it that for no reason. I'm creating from the random subpackage of NumPy, I'm creating 100 uniform random numbers. That's what rand does. That's 100 uniform between 0 and 1 random numbers. And then I'm going to take for y, I'm going to create a line, basically 5 times x, for that scattered random data, and then I'm going to add noise to it. I'm going to add uniform noise to it. And I'm just going to use the plt.scatter and give it the x data and the y data, and then I'm going to create that scatter plot. Now there's different types of things you can play with the scatter plot. So you can play with the size of the objects. You can use S for that. So if I make S, let's say 25, just so you can see what it is. I think they look a little smaller there. If I go up to 50 this will just change the marker size. See, they get a little bit bigger. You can also change the marker. Instead of being circles, which is the default, you can make it into squares. I believe that's, I think, just S. So there you go, they look like squares now. You can there's all sorts of other options. Again, this is where the tutorials and other types of documentation are useful to review because there's a lot of options for you. So you can make the color red if you want it as well. And I think D might be for diamonds. Let's see. Yeah, D is diamonds. So you can play with this. It's really good for you to just you can play with and kind of just experiment. Like, well, what would it be? But you can definitely look at the documentation. I think even if you just again hover over scatter and look at some of the information and scroll through it, you'll see types of options that you have for it. But I like looking at the official documentation outside of the Colab environment. So that's it for this part of the video. In this very last part of this lecture video, we will be talking about subplots and 3D plots using the MPL toolkits package within matplotlib. Now, the subplots, you don't have to really worry about doing things with 3D plots. You can do subplots with 2D plots. I'm just showing them in conjunction with the 3D plots here. So subplots are one way to arrange multiple plots into one figure. So each subplot will define its own set of axes within that figure. The subplot function takes the arguments in rows, in columns, and then the plot number you want to use. So you may find the reference I have here to be a useful reference when determining how you want to index an array in 2 or 3D. So this is a mesh grid reference. I highly recommend that. It's something just when you want to generate arrays of data in 2 or 3D for visualization, the numpy.meshgrid is a very useful reference for that. So for simplicity, I'm not really doing anything too complicated initially. I'm creating a matrix A that's using the range function, and I'm just reshaping this range of data, which is going to generate the numbers from 1 to 12, because it's 1 up to but not including 13. And so that's 12 numbers. I'm going to arrange it as a 3 by 4 matrix. I'm going to create a figure. As you can see here, fig is equal to plot.figure. I'm giving it a figure number here. That could be done. I was talking about this like num equals this. So I'm just doing that here, num equals 1. I'll just go ahead and do it so it makes more sense. That's what num is. I'll leave it there in the notebook. If you're watching the video, it wasn't there initially as that keyword. I was just putting 1 there, but that was the number variable. And I'm also specifying the fig size. So it's just with a 10 and a 6, and you can play with these numbers. I highly encourage you to do it. What happens if you make it 6, 10 instead of 10, 6? What if it's 8 and 8 or 12 and 5? Play with it and see what you like for the fig size, because that's going to depend on how much you've zoomed in to Colab, like your web page is zoomed in, the size of your monitor, and so on. I'm also encouraging you to try commenting and uncommenting out parts of the code and see what happens. One of the things I'm showing you is I'm going to create axes for each of the subplots. And I'm going to add subplots in a 1 by 3 array. And then instead of Python indexing by 0, you index by 1 here. So that could maybe be a potential source of confusion or error. So the first plot is indexed by 1. So in a 1 by 3 array, the first plot, which will be the one basically on the left in my 1 by 3 array, will be assigned to axis 1. And then I'm commented out this one, but you can go ahead and uncomment this if you like. And then axes 3 are going to be the third plot. So this is the rightmost one. So I'm basically leaving the second set of axes just kind of not generated. I'm actually not even creating any axes associated with that middle plot in a 1 by 3 array. So this is just going to put some space between my plots. There's really no reason to do this other than to just show you that I can. If you uncomment this, you could see what happens with that. It will be an empty pair of axes that are generated. Now, when you start using the axes to generate, to plot data inside the axes, you don't use the plt.plot command anymore. Things are a lot different here. So you could use plt.ylabel, plt.plot. You often use set label, set xticks. Like there's things that you do when the axes that they use set. You're setting specific things within the axes. And if you didn't have subplots at all, you would just use plt.plot or plt.ylabel. You'd still do like axes.plot or axes.scatter, but the various other things in terms of like setting a title, setting an axis label, and so on, you do use set underscore, and then the thing that you would usually just have plt.ylabel, plt.title, and so on if there was just one set of axes. That's just something to be aware of because it does come up when you start working with subplots. So I think you can read through this and kind of see what's going on. I'm setting a Y-label to be average. I'm just plotting over the array, like with this array of data, with the subplots. I'm creating the scatter of this array data, and I'm plotting this mean data. I have this axis command here that's harkening back to something we saw in a previous lecture. I highly recommend, I'm going to fix some of this code commenting before I post this in terms of the formatting. I recommend you add a code comment here that explains what this is doing. I'm also completely commenting out this. I don't like using a docstring to comment things out. I'm just showing you something that we can do. We're actually going to discuss docstrings in the next module, so I'm just using them here to get you used to it. They're usually really only belong at the top of a user-defined function or a class or an object that you're creating. So this is not really an appropriate use of them. I am just showing it to you as an option. Like sometimes it's just nice to be able to quickly comment out a whole chunk of code using 3 ticks on either side of it, but that's really a bad thing to do. I would often just recommend just, collect all the lines, just shift, copy, collect all of them in this way. Let's grab them all. And I usually do control backslash, that comments them out. And then if you do a control backslash again, it brings it back. So, or excuse me, that was /, control /, and then control / again will comment and uncomment out what's going on there. So anyway, something to just be aware of, but feel free to just remove these comments entirely and then just plot that other set of axes. But if you run all of this, then this is what you'll see. So that middle plot, right, I commented out, so there's just blank there. If you uncomment out parts of it, like leave this commented with a docstring, which again is kind of an inappropriate way to comment, and then you, let's say, bring that back and you run this, you will see this empty set of axes that are here. So this is stuff you should just play with it yourself. You know, play around with it. If that's commented out and then you uncomment this, that's going to be a problem. Because these axes are not defined. So, you know, you can see you'll get an error, and you should get an error. You can see what happens if you don't have the tight layout. I like the tight layout. It does spacing better between multiple plots, especially when I'm saving plots to file to include in papers I'm writing or in presentations I'm giving. If you comment out the fig.tight layout, you can notice a little bit of a difference, like just in the sizes of these things compared to when I had it here and how they present, like just the spacing of it. So I generally think that this it does a better job of managing the white space in the figure around the axes, around the plots. So that's a very common thing for me to use when I'm creating plots. So that was just the subplots. I'm doing it actually separate from the 3D plots, although I do some subplots for the 3D plots below. Here I'm creating arrays of X and Y data. I'm using that mesh grid function that I mentioned at the very beginning of this part of the video to create 2D arrays of X and Y data, because then I'm going to plot like this matrix A as if it was a function of the X and Y data. This is just for illustration purposes, nothing more. But here is where from that toolkits, the MPL_toolkits, mplot3d, I'm going to import the axes 3D. From the axes 3D, this enables the 3D plotting. So you'll see what happens with that. I'm also importing for something for color maps so that I can create some different color maps. But when I want to do this projection 3D, if I don't have this in here, then that's a problem. I've already imported it, so it will work. But if you were to, let's say, restart the runtime, the kernel, and then run through all this again, but you had this commented out and you were trying to run it, then this line would give you some errors, or should give you some errors. It would certainly happen in a lot of other environments. I believe in Colab it's the same thing. But this is just something you should just kind of go through, and you can see I'm creating frame plots. I'm creating a 3D scatter plot. I'm creating just a surface plot. So with all those different plots, you can just see the options here. You actually don't need this plt.show command. That's what you would do if you were doing it in a Python script. And just in a Jupyter notebook, it's going to plot that. Again, if you were in other environments, you might need to use the matplotlib inline or matplotlib notebook magic commands. But in Colab, it's just going to plot it out. By the way, if you look at all this, like I'm just going to run this again and show. There we go. I got rid of that kind of annoying little thing that we saw there. And I'm just doing that tight layout. I did it with the figure. I believe it's the same thing. If I do plt.tight layout, it should be the same. Yeah, this is creating that's just some warning. That has nothing to do with it, but let me just run this again. Just do Control-Enter that time. There we go. Got rid of that, whatever that warning was, is deprecation warning. So this is something just you need to play with it a little bit. You can see I'm setting the X labels, setting the Y labels. Again, using the set underscore before the Y label is because I have these different axes I'm plotting in. If I didn't have subplots, then I would just be using plt.x label, plt.y label. But as soon as you have subplots, you have different sets of axes, and you need to set the labels for each of those individual axes separately. So that's just something you got to get used to when you have subplots. That's kind of it. After this, I'm asking you to do this other activity. It has nothing to do actually with subplots, but just using some curve fitting and plotting tools. There's a solution video for it. And I have several sets of instructions here for you to follow through, as well as lots of code comments to help kind of orient you about the things you need to fill out to do that activity. And then there's a summary activity. That is it for plotting. It was a very brief tutorial. I just wanted to kind of give you a very quick overview of 2D plotting commands, the various ways you can customize them, and also doing some subplots and 3D plotting. So that's what we've seen. We've actually seen a lot in a short period of time within this notebook, and we're going to see some more advanced plotting, annotations, and visual storytelling in Module 4. But we have kind of all we need now to go to Module 3, and we'll come back to quite a bit of plotting later on in the course.